So worksheets 6 through 9 are due on the 2nd. Homework number 4 will also be due on the 2nd. That's after Thanksgiving. If you have any missing assignments you want to turn in, you can always turn them in late. The presentations and papers are going to be due on the 4th. Make sure your topic has been accepted. If it hasn't, submit another topic. Make sure you didn't choose a topic from the list of claimed topics. The order for presentations. You're going to do a 2-page paper on the topic and a 5 to 10 minute presentation on the topic. Oh, oops. That is a mistake from a previous year. Copy the dimensions. So the presentations start on the 4th. They'll be in class. Make sure you have your slides available. You can bring them in on a USB stick. You can submit them in advance to me so I can download them on the day. The schedule for all presentations is now up on Brightspace as of today. Sorry I was so late about it. I forgot to make it visible. Actually on this class I had to stick a few numbers in there as well, and the exam number 4 will also be on the 2nd. Yeah. Any questions? All this stuff is after Thanksgiving. So we were discussing weather. We talked about physical weathering and we started to talk about chemical weathering. Chemical weathering is a process that alters the internal structures of materials by removing or adding elements. Generally what happens is something chemically interacts and breaks down the material. So the most important agent is water. So oxygen and water dissolved in water can oxidize materials. Things can basically rust. Carbon dioxide in water also forms carbonic acid, and that alters the material as well. It is acidic and can dissolve certain minerals. And also water can just dissolve certain minerals. So there's various processes that happen. Water can dissolve various minerals. Minerals can be transformed from one form into another. This is how feldspars turn into clays. So it changes the chemical weathering changes the chemical composition of rocks and minerals, principally through reactions with water. The 2 most important factors in chemical weathering are water and temperature, because water is the primary actor in chemical weathering, and all chemical reactions generally happen faster at higher temperatures. So chemical weathering is most efficient in hot, moist, tropical climates. So Southeast Asia, for example, has a lot of chemical weathering. It also, because of the hot, moist tropical climate, it has a lot of plants that also generate acidic compounds that assist with chemical weathering. Limestone, which is a common rock at the surface, readily undergoes chemical weathering. Limestone dissolves, it forms caves and structures like this. Now, granite is an example of how granite will weather. So potassium feldspar will weather into and form clay minerals, soluble salt, potassium bicarbonate, and silica in solution. So small amount of silica in solution. Quartz, on the other hand, remains substantially unaltered. So the quartz crystals remain behind and basically become sand. The potassium feldspar turns into clay, and then there's other things as well. So the weathering of silicate minerals produces insoluble iron oxides and clay minerals. So quartz turns into quartz grains. Maybe there's some small amount of silica in solution. Feldspars turn into clay minerals with silica, potassium, sodium, and calcium in solution. Amphibole turns into clay minerals and iron oxides with silica, calcium, and magnesium in solution. Olivine turns into iron oxides with silica and magnesium in solution. Another thing that can happen with weathering is that it actually turns things round. Because at an edge, weathering can attack from both sides. At a corner, it can attack from three sides. This wears down the sticking out pits. So this will steadily generate rounded rods. Weathering will attack only a face only on one side. So a flat surface can only be attacked from one side, while an edge can be attacked from two and a corner from three. And this will round corners and eventually form round rocks, like this rock here, which has been spheroidally weathered in place. Because weathering works inwards from exposed surfaces. Now, the chemical weathering of limestone is a significant factor in a lot of geography and topography. Limestone is made of largely of the mineral calcite. Normal rainwater will react with carbon dioxide in the atmosphere to form a weak solution of carbonic acid, H2CO3. H2O plus CO2 is H2CO3. And the more CO2 the water comes in contact with, the more carbonic acid is formed. This is why seltzer water is always a little sour. And as water percolates through the soil, it can react with even more carbon dioxide released by bacteria. So if you just add carbon dioxide to water, it becomes slightly acidic. When the carbonic acid comes in contact with the calcite, CaCO3 in limestone, they will react to form CaHC3CO3-2. So calcium bicarbonate. Calcium bicarbonate dissolves readily in water and gets carried away in the solution. If the water evaporates, the calcium bicarbonate will can lose some CO2 and turn back into calcite. That's how stalactites and stalagmites form. Now, most chemical weathering in limestone occurs along fractures where the most water flows, and given enough time, underground caverns can form, and the cavern ceilings can collapse, creating sinkholes. We'll go into more details about that process in the next chapter. Yeah, in chapter 9. And chemical weathering is most rapid in areas with high temperatures and abundant moisture. In very cold areas and very polar regions and very dry areas, deserts, chemical weathering is relatively sluggish because there's either not enough water to do the chemistry with, or it's so cold the chemistry doesn't happen very quickly. And here's a bit of showing various types of chemical weathering.
The second kind of weathering is called chemical weathering. Chemical weathering causes changes in the rocks from the reaction of different chemicals on the surface of the rocks. One common example of chemical weathering is called oxidation. If we were to leave an iron nail in a cup of water for a few weeks, a chemical change takes place. The nail gradually becomes coated with a dark red substance we call rust. Rust is oxidized iron. Here we see the difference between a shiny new nail and an oxidized nail. This rusting or oxidation deteriorates any surface on which it reacts and will eventually cause it to break down and fall apart. The mineral iron is present in many different kinds of rocks, and oxidation can break down these rocks if they're exposed to water for long periods of time. But are there other ways in which rocks can chemically weather? These rocks are covered with a plant called lichen. They illustrate another example of how the chemical weathering process takes place. The lichen actually secrete a mild acid which can dissolve or eat away the surface of the rock. Carbonic acid, a mild corrosive agent, can form when water and carbon dioxide combine naturally in the air or below the earth. Underground caverns like this are one of the most spectacular examples of the effects of weathering caused by carbonic acid. This cavern started out as small openings below the Earth's surface where water seeped in. The water combined with carbon dioxide from decaying plant material in the soil to form carbonic acid. As this acid dissolved the rock around it, the pockets gradually grew in size. The force of gravity, combined with underground streams, carried the dissolved rock fragments away until finally a huge cavern was formed. This, along with the continuous seeping water, caused the cavern formations to grow even stranger as time passed.
So certain rocks and minerals are more resistant to chemical weathering. And the effects of modern chemical weathering can be readily observed by viewing cemetery headstones, because different headstones are made of different minerals, rocks. So you'll see that marble is composed of the same, because marble is composed of the same mineral as limestone, and therefore it will readily react with slightly acidic rainwater. You'll see that marble headstones, marble things in a cemetery are much more worn down than granite ones. Granite ones will be much sharper and much clearer, while marble ones will be more rounded, because granite is much more resistant to weathering than marble is. So here's a sort of summary of weathering. You have mechanical disintegration, which has things like frost wedging, the freezing, thawing of water in cracks, salt crystal growth, where salt crystals grow from evaporated salty water, mechanical exfoliation, where rocks expand and crack as the overlying rocks are removed by erosion, root penetration, as powerful tree roots grow in rock fractures, thermal expansion and contraction, which is the enlargement and reduction of crystal structure in response to heating and cooling, and abrasion, where rocks and minerals collide in a moving current. And then you have chemical decomposition, where it's a change in chemical properties. You have dissolution, where various things dissolve, soluble compounds such as limestone get dissolved. This produces caves. Oxidation, where mineral ions combine with oxygen to form an oxide. This forms rust. And hydrolysis, where H- ions displace other ions to form a different mineral. This is common with feldspars. This is how clay minerals form. And another thing that can happen is what's called differential weathering. This is caused by variations in composition, where certain rocks weather more than others. And this can lead to some spectacular looking rock formations and landforms. So other factors that contribute to differential weathering, things like the characteristics of the rock, mineral composition, the solubility, the physical features, and also climate, temperature, and moisture can have a big effect. So here we have an example of a hoodoo, which is a monument to weathering, where there's this cap that's more resistant to weathering, and it preserves this sort of shaft underneath that is less resistant. So here's a video about the sort of differential weathering. In a particular place you can see them is in the southwest corners.
Hello, I'm Michael Collier. You know, rocks don't last forever. They break down, they weather at the Earth's surface. That's the Misty Badlands down there. It's a moonscape in northwest New Mexico. It's a great place to get a bird's eye view of rocks being sculpted by weathering. On this field trip, we're going to look at strata that were deposited during the time of the dinosaurs. Different layers within these sedimentary rocks weather away at different rates. The result is this wild collection of unexpected shapes. We'll learn that weathering is caused by mechanical or chemical forces. Water, fire, even human beings can hasten the processes of weathering.
The BSTI lies 30 miles south of Farmington in the heart of the San Juan Basin. These 75 square miles of the Fruitland and Kirtland formations are filleted open, mostly by water, sometimes by wind, exposing 70-million-year-old sedimentary rocks, sandstones, shale, and mudstones. During the late Cretaceous, an inland sea occupied this part of North America. Rivers and deltas on the edge of the seaway were home to fish, turtles, crocodiles, and early mammals. How many of those animals do you think you would recognize today? The Fruitland Formation is riddled with fossilized bones as well as petrified wood. The overlying Kirtland Formation is busting its buttons with dinosaur remains. Now, as layers of the BSTI are peeled back, bones are exposed. In fact, a new species of Tyrannosaurus was excavated here not long ago. The BSTI Badlands sit 6,000 feet above sea level. Winter nights are cold, but there's plenty of sunlight to raise daytime temperatures. Any water that creeps into rock crevices repeatedly freezes and thaws, expands and causes cracking in a process called frost wedging. Blocks are pried into smaller, angular pieces, a type of mechanical weathering. When minerals that form deep underground become exposed at the surface, they must adjust to new conditions of lower pressure and temperature. Exposed to the sun, or soaking in the rain, rocks begin to disintegrate. Feldspar crystals decompose into clay. Quartz crystals break down into grains of sand. The BSTI is a stark desert, but a few springs do flow here periodically. Salts can be dissolved in the water and then deposited into crevices. As salt crystals grow, they enlarge cracks in the rock and, like freezing water, break it apart. Also, chemical weathering is greatly accelerated by the presence of acid in groundwater. This might happen when rain mixes with carbon dioxide from the atmosphere to form carbonic acid, or when minerals like pyrite decay into sulfuric acid. Can you think of other examples of acid hastening weathering? The Fruitland Formation is a stack of hard and soft layers, sandstones on top of shale, mudstones on top of coal. Sometimes a strangely shaped hoodoo forms when a cap of sandstone shields the underlying shale from rain. In this way, sandstone and shale, crumbling at different rates, exhibit differential weathering. Weathering and erosion are separate processes. Weathering breaks rocks down. Then erosion, powered by water or wind, carries grains away. But the two can be intertwined. As erosion carries away particles of rock, fresh exposures are subject to renewed weathering. A surprising variety of agents cause weathering. Animals can be prodigious burrowers, busting rocks apart as they dig. Fire is another agent. The Fruitland Formation is riddled with coal seams, some of which burned while still underground. Nearby layers of siltstone were baked and broken into red clinkers. In the last few hundred years, humans have become significant agents of weathering. It's true that the BSTI Badlands are a protected wilderness, but by conservative estimates, the Fruitland contains 90 million tons of coal, a fact not lost on power companies who would burn it to generate electricity. When miners dig up the coal, they also cause weathering. Can you think of other human activities that might influence weathering on a geologic scale? Which term best describes the process that created the oddly shaped rocks at BSTI Badlands? Unloading? Differential weathering? Exfoliation. Rocks at Bisty Badlands were created by differential weathering. How can plants facilitate weathering? As roots grow, they're able to exert tremendous pressure, enough to break rocks. This is an example of mechanical weathering. But plants can also increase the acidity of groundwater, which leads to chemical weathering.
So we've talked about weathering. Let's talk about what is made from that weathered material, soil. Soil is sort of an interface. It's a boundary where parts of the system interact. And it's the combination of mineral matter, water, air, and organic matter. So the mineral matter in soil is called regolith. This is the rocks and mineral fragments in the soil. This supports the growth of plants. For it to become truly soil and not just regolith, you need to add organic matter. So what is soil? It's about 45% mineral matter, about 5% organic matter, and then about 50% is a mixture of air and water. And the amount that's water and air varies depending on its height generally. There's more air at the surface, it's full of water down below. So when we talk about soil, soil has a texture and a structure. Texture refers to the portion of different particle sizes. So sandy soil, sand is larger particles, silt is smaller particles, and clay is the smallest particles. And loam, a mixture of all three sizes, is the best suited for plant life. And when people talk about different types of soils, they organize them by how much is sand, how much is silt, how much is clay. And so there's what's known as a soil texture diagram, as you can see here, percent clay, percent sand, and percent silt. And for any point on this, it will add up to 100%. So if it's got lots of clay up here, this is called clay soil, silty clay. As it gets more silty clay, clay loam is a nice mixture, sandy clay. Then we have sandy clay loam. Loam is the mixture of all three down here. I mean, the middle is here, but we want a little bit less clay than all. And then we have, sandy loam, loamy sand, and sand down in the high sand area, loam, silty loam, and silt down in the high silt area. Now, the structure of soil is based on how that soil particles clump together to give soil its structure. And that's based on how soil will break apart. There's 4 basic soil structures: platy, prismatic, blocky, and spheroidal. And they determine how easily soil is cultivated. I guess I don't have pictures. There are pictures in your book, I believe. Well, platy soil breaks into sort of flat places, blocky into blocks, spheroidal into sort of balls, and prismatic breaks into more angular pieces. Now, the controls of soil formation is based on, there's both these are some of the controls, some of the factors that go into the formation of soil. There's 5. So the first of these is the parent material. Is it residual soil, where the parent material is the bedrock? The bedrock is breaking down in place and turning into soil. Or is it transported soil? The parent material has been carried from elsewhere and deposited. One of the most important factors is time. This is important in all geologic processes, and it takes a certain amount of time to evolve for different soils, and the amount of time it takes is different for different types of soil. The climate is important, so the temperature, the amount of water, things like that. And plants and animals are an essential factor. Various organisms will influence the soil's physical and chemical properties, and they will furnish organic matter to the soil. Because without organic matter, it's just regolith. And lastly, the topography has a major effect. The angle of the slope it's on, so steep slopes often have very poorly developed soils because stuff rolls down the slope. Your optimum for developing soil is a flat, undulating upland surface. And the orientation, the direction the slope is facing, can influence the soil's temperature and moisture, which can influence how it develops. So here, for example, there's no soil development because of the very steep slope. Here we have a sort of level flat area with transported soil from deposits from streams, makes great soil. And then here we have residual soil being developed on top of bedrock. Now, the way we describe and classify soil is with the soil profile. The soil forming processes, the processes that create and form soil, operate from the surface downwards. So there are several horizons or layers of soil. And in a typical temperate region, you'll see these layers. You have layer O, which is organic matter. This is dead plants, stuff like that. Layer A is beneath layer O. It's got a mixture of organic and mineral matter. Below that is layer E, which is where you have alluviation and leaching. This is where matter is being extracted by water and leaching down to lower layers. And that accumulates in layer B, which is the zone of accumulation. So the matter, the various materials leave layer E and accumulate down in layer B. And below that, there's partially altered parent material, layer C, which is sort of the top of the bedrock where it's breaking apart into pieces. You can see this sort of here. And then you have unweathered parent material. So partially altered, partially weathered material. The C horizon, that's the C horizon, the B horizon, that is the sort of the subsoil. There's an accumulation of clay transported from above. The E horizon is a little more barren because it's the zone of alluviation and leaching, where material gets moved down into the B layer. The O horizon is the loose and partially decayed organic matter, very thin, and then above that, below that is the A horizon, which has mineral matter mixed with humus or organic matter. That's the topsoil. So if you've heard about topsoil, this is the topsoil, O and A, and then the E horizon, sort of this leaching layer, and then B and C is the subsoil. Well, B is the subsoil, and then C is sort of below that, and the true soil is O through B. So here's a short video about the various soil horizons. They're not always as clear as they are in that
back
picture.
for another smart figure. After watching this video, you should be able to describe the sequence for the different horizons that are found in a typical soil profile, and you should explain why those different horizons are where we find them. So soil is really important. It's the substrate in which we grow the food that we eat, or we grow crops that we feed to livestock that we then eat. Soil is essential for feeding the human population, so it's important to know something about it. Soil is about half solid material and half empty space. The solid material basically is divided up between a majority of mineral matter, so these are rock fragments and mineral grains, chemical residues, things like that, and then a smaller proportion that is organic material or humus. The rest of the soil is empty space, and that empty space can be occupied by air or water depending on the climatic conditions at the time. This is a look at a typical soil profile. Soil profiles vary from place to place, but typically you'll see these general horizons. We start off at the top with the O horizon. The O horizon is basically dominated by organic materials, plant fragments and things like that. Below the O horizon is the A horizon, and this is where we find mineral matter that's been mixed in with some humus. Below the A horizon is the E horizon, and the E horizon basically forms when rainwater percolates down through the soil and it leaches out material from the mineral matter in the A horizon and the E horizon. Basically, it's dissolving away material and then carrying it down through the soil profile as it percolates in. Some of that material ends up accumulating at the B horizon. So the B horizon basically is the spot where there's accumulation of clay that's been transported in from above. So some of the clay that you find in the B horizon didn't start off there, it was transported in from, say, the E horizon or the A. Now, the O horizon and the A horizon together are called the topsoil, and they're so rich in organic material so that they appear quite brown, usually a very dark color. The B horizon is often known as the subsoil. And together, all the layers that have been discussed so far, O, A, E, and B, are referred to as the solum, or the true soil. Below the true soil is the C horizon. This is partially altered parent material, so basically rotten bedrock. And then below that is the bedrock itself, unweathered parent material. Here are two examples of soil profiles, one from South Dakota on the left and one from Puerto Rico on the right. So you can see that there are certain horizons that will stand out to the eye. So here, for instance, you can see that O horizon up at the top. You've got the A horizon that's still dark. So together, those two are the topsoil. Here's the E horizon that's been eluviated, so it's had material leached out from it, and then the B horizon below that. The example in Puerto Rico is more gradual, where you see basically a change in color from top to bottom, but definitely you can still see the organic material is at the top. How about this example here? Is this something that you're ever going to be likely to see out in the real world? And if so, how would it form? Hopefully what you said is that this is an unlikely situation to be stable in a soil anywhere in the world. But you could actually get something like this, where you had an earlier well-developed soil profile, and then maybe a flood or something deposited a bunch of mineral matter on top of it, and then new organic material accumulated up top. So you could end up getting a preserved topsoil layer in a soil profile, but it's not going to last very long. You know, once the processes of alluviation and leaching go to work on this, you're going to end up rapidly reorganizing this stuff into something that looks more typical. Thanks very much for your attention. This has been another Smart Figure.
So the way we classify soils in the United States is called the soil taxonomy. It emphasizes the physical and chemical properties of the soil profile, and the names of soil units are combinations of syllables of Latin and Greek origin. And there are a ton of them. So here is sort of global soil regions, various different soils in various different places. So around here we have sort of dark green mollisols. In the southeast, they have sort of yellow utilisols, I think. You know, the Sahara Desert has entisols and viridisols. So there's various different types. Now, soil erodes. It gets carried away by various things. And human activity can make soil erosion more severe. Now, the erosion of soil is part of the recycling of earth materials. There's sort of natural erosion that constantly occurs where soil gets picked up and carried to other places. The natural rates of erosion depend on things like the characteristics of the soil, the climate, that you're in, the slope, you get more erosion on steep slopes, the type of vegetation. If you strip off all the vegetation, the roots aren't there to hold things in place, you get more erosion. Other vegetation helps hold things in place quite well. Now, some of the processes that erode soil. Water is the biggest source of erosion. Raindrops falling from the sky will dislodge particles of soil, as shown here. They can strike the surface at velocities approaching 35 kilometers an hour. And when they strike an exposed surface, soil particles can splash as high as 1 meter and land more than a meter away. And then flowing water, if you have water flowing across the surface, so runoff, will carry away soil. And 2/3 of all US soil erosion is by water. Now, wind erosion occurs primarily when it's very dry. One of the most dramatic cases of wind erosion was the Dust Bowl in the 1930s, where a drought combined with the fact that we had plowed and removed all of the prairie holding down the soil across large portions of the central US, led to very dry soil that we had plowed and removed everything holding it in place. So we loosened it up. Basically just got picked up and blew away. And it was called the Dust Bowl because huge amounts of soil were topsoil were blowing away on the wind. Now, what can we do to control the erosion of soil? We can leave steep slopes undisturbed. Don't cut into them, don't remove vegetation, things like that. We can plant crops in terraces so that when we plant, because when you plant crops and you plow and such, you remove all the vegetation, you actively loosen up the soil, which increases erosion. But if you terrace crops, all of your crops are planted on level, flat surfaces, so there isn't any natural slope for to carry the soil away. You just make a stair-steppy structure. You can use grassed waterways to control the flow of water and allow water to flow out of fields along these grassed areas. And you can have windbreaks made of trees around your fields. So here are some examples of that occurring. So crops are planted in strips along the contours of the hillside with these grass drainage areas and grass along the drainage to hold the water, to handle the water runoff and prevent erosion where the water runoff is. The strips along the contours help control water runoff, which helps control erosion. So this is sort of some methods for conserving soil. Terracing is expensive because you need to actually make a stair-stepping structure, but it is a very common and traditional way to plant on steep slopes. So let's talk about mass movement on slopes. This is stuff moving due to gravity. Mass movement is the downslope movement of rock, regolith, soil under the direct influence of gravity. It is, in general, stuff rolling down the hill. It can be fast or slow. Gravity is the main controlling force. And this will develop landscapes over time. It will change landscapes. It will even out landscapes as material moves downhill and hills lose material. And slopes can and do change throughout time. And a lot of human-created slopes tend to be quite steep. And that leads to often heavy cases. We have to act to reduce mass movement. So mass movement or mass wasting is a general term for the downslope movement of rock and soil under the influence of gravity. Gravity tends to pull material down and friction tends to keep the material stationary. One of the big factors that influences when this is going to happen is water. Water is heavy. And so it adds weight to the material, makes it more likely to roll down the hill. And enough water will also reduce the friction between the particles of the material because it'll spread them out. There'll be less friction. They're not going to stick as well. So in general, the presence of water will promote the failure of slopes. So, you're likely to get this after rainstorms, things like this. So a landslide is a popular non-technical term used to describe all material that's moving downhill. This can be a significant natural hazard causing loss of life and tremendous damage. So here's a debris flow in the Colorado Front Range. And when material gets saturated with water, this will destroy particle cohesion and water adds weight. So here, dry grains are bound together by friction with each other. Now, a small amount of water, like you use when you're making a sandcastle, increases friction, increases the cohesion among the sand grains. It's complicated, but a little bit of water, because water is really strongly attracted to itself, will help pull the sand grains together and increase cohesion. But once you add enough water, the grains will separate and everything will collapse. So water is a little confusing, like the amount of water you add, a little bit of water helps hold things together, but a lot of water causes things to fall apart. Now, the over-steepening of slopes will cause things to also roll downhill. So if you have unconsolidated granular particles, just stuff, any sort of powdery grains in a pile, they will assume a stable slope that's called the angle of repose. So this is the angle of repose. The angle is different for different materials. Some material is going to have a steeper angle, some material is going to have a more shallow angle. And they'll naturally form sort of a angle, things at the angle of the repose. If you go steeper than the angle of repose, stuff will start to collapse and roll down until it gets to that stable state of the angle of repose. Another important trigger for our Earth is earthquakes. So some triggers for our mass wasting: the removal of anchoring vegetation. Vegetation helps hold things in place, anchors the soil in place, keeps erosion from occurring, but ground vibrations, if you remove that, it makes it much more easy for erosion and this mass wasting to occur. And the vibrations from earthquakes can loosen material and shut off collapses and the movement of stuff downslope. So here's an example of landslides, destruction caused by an earthquake, where material came down this steep slope. Now, there are several different types of mass movement. Generally, they're defined by the material involved. Is it debris, mud, earth, or rock? And the movement of the material. Is it a fall, like a rock fall of material? A slide, material moves along a well-defined surface, like a rock slide, or a flow, the material moves like a viscous fluid. And then the rate of movement. Is it fast or is it slow? Fast catastrophic mass wasting occurs in two basic sort of forms: landslides, with the rapid downslope movement of large blocks of weathered material. If large volumes of rock involved, it's called a rock slide. And mud flows, where material that's saturated with water flows down slope like a thick viscous fluid. Now there's slow methods of mass movement as well. Slump is the sort of large chunk of material, slow downslope movement of an essentially unbroken block of overburden. So this is, you have a big chunk of material sort of slide slowly down. Slumps leave a curved depression in the slope, marking the detachment zone. And then creep is the very slow, imperceptible particle by particle movement of debris down a slope. This is caused by the heating and cooling, where material moves out, and then down, and then out, and then down. And it can be too slow to see the movement, but the results over years can cause things to tilt over, trees to grow bent, things like that. And abundant vegetation and its root structure help deter all types of mass wasting. So here's a short video about different types of mass movement. mass waste.
Mass movement is the movement of surface material downhill due to gravity. The loose surface material is known as regolith. There are four main factors which influence mass movement. Gradient, the steepness of a slope. Water, this is generally in the form of rain, making the regolith heavier and more unstable. Human activity, such as the building of roads and railway lines which undercut a slope. And vegetation, the roots of trees help to bind the soil together to make it more stable. Soil creep is a very common form of mass movement and can be seen in the landscape all around us. Any second now. Still no? That's because soil creep is a very slow form of mass movement, often as slow as 1 to 2 centimeters per year. Similar in a way to the movement of tectonic plates, you cannot see the movement, but can see the impact of soil creep over time. Tree trunks bend and telegraph poles lean downwards. Fences may collapse and walls can have soil build up behind them before eventually bulging and collapsing. On grassy slopes, the soil may form into steps known as terracettes. As soil creep bends the lower trunk of a tree, it will begin to lean over. However, the trunk will then straighten as it continues to grow upwards. This is to maximize the amount of sunlight that the tree receives. Landslides occur when loose rock and soil move down steep slopes in upland areas. The removal of vegetation and the undercutting of slopes to build roads and railway lines can combine with heavy rainfall to lead to a landslide. A landslide scar is often left behind as the surface layer of soil and grassy vegetation can be removed. Like other fast forms of mass movement, landslides can cause significant damage and destruction to animal habitats, farmland, and human settlement. Mud flows are a very fast form of mass movement. They can occur in areas of high rainfall with steep slopes where vegetation has largely been removed, such as on farmland in the west of Ireland. Heavy rainfall can make the soil saturated and unstable, creating a fast-flowing river of mud that can flow freely and travel several kilometres downslope. Bog bursts are similar to mud flows, but occur in upland areas where peat is found. A lahar is a volcanic mudflow and generally can lead to more casualties in an area surrounding a volcano than lava. When volcanoes are active and erupting, they produce a tremendous amount of heat. If the summit of a volcano is snow-capped, the snow and ice will melt. This will mix with the volcanic ash and soil on the mountain to form a volcanic mudflow. The Nevada del Ruiz volcano in Colombia erupted in 1985, creating a lahar which moved downhill at over 80 kilometers per hour. Over 20,000 people were killed and 5,000 homes destroyed in the town of Armero, which lay at the base of the volcano.
So a slump is a relatively rapid movement along a curved surface. It occurs over steepened slopes, but it's a big chunk sort of slides down. You have this big block, and you leave behind a scarp. You might have an earth flow below. A rock slide is a slide of blocks of bedrock down a slope. It's a landslide made of rocks. A debris flow or a mud flow is the rapid flow of debris that's saturated with water. It often is confined to channels, because, you know, it flows like a liquid. And debris flows composed mostly of volcanic materials are called lahars, and they're a particular danger because when volcanoes erupt, they produce heat and a whole bunch of poorly consolidated ash and dust and such, which can then get saturated and flow downhill. So here's a mud flow from 2005 in Southern California. You can see where it drew material from, and it flowed down into this residential area. An earth flow is a rapid flow, typically occurs on hillsides in humid regions where water saturates the soil. And sometimes you get the earth flow at points of liquefaction, where you get liquefaction is an earth flow associated with earthquakes, where the earthquake vibrations cause the water to saturate the soil and allow it to flow more easily. Creep is the very slow movement of soil and regolith downhill. It causes fences and utility poles to tilt, but it's, you know, centimeters a year. And solifluction is the very slow movement in areas underlain by permafrost. This is called by the upper active soil layer melts and refreezes and becomes more fluid and less fluid, and sort of oozes down hillsides, becomes saturated and slowly flows over a frozen surface beneath it. So here is about creep. You have creep caused by freeze-thaw cycles, where you get expansion caused by freezing, and when it contracts, the material falls downwards, and each step moves a little bit down the slope. So here's a video of
Hi there, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe how creep happens and what some of the consequences of creep are. If you're wondering what creep is, here's a picture of it. No, not the guy in the middle of the picture. Notice that there's this tree trunk here that has this extraordinary shape to it. It has this big sort of J-shaped tree trunk. Why did that tree grow in that bizarre fashion? Well, it has to do with creep. The idea behind creep is that soil experiences freezing and thawing. So there's some water in the soil, and if we pay attention to an individual particle, like this guy right here, and we watch what that particle does when the soil freezes, we'll learn something. So let's go ahead and make it really cold at night, and that ground freezes. It ends up pushing that soil particle out away from the hill. Notice that it's moving out, not up, okay? So it's moving out. And then the next morning, when things thaw out again and it warms up, it ends up dropping down due to gravity. So another night, freezing pushes it out. The next morning, it falls down due to gravity. Freeze, thaw. And you can get the idea here. Basically, if you do this enough times, you end up moving that particle a long distance downslope. However, we're only talking about millimeters or maybe a centimeter or so at most in terms of these freeze-thaw cycles. So it's not moving very far, very fast. It's only over the long term that this effect builds up and manifests itself as creep. How do you know that creep has taken place? Well, let's take a look at this diagram from your textbook. Here are some of the symptoms of creep. You'll notice that we've got bent rock layers here. So the bedrock layers, they basically curve in a downhill direction when they get up into the zone of creep. We've got the curved tree trunks, which are sometimes described as being J-shaped or pistol grip shaped, like the pistols that they use in Pirates of the Caribbean, those old Buccaneers pistols. Here's a tilted fence and a broken retaining wall as well. One other thing that's not labeled on here are these tombstones. What would be the effect of creep on tombstones, do you think? Well, if you suggested that they're going to tip over in a downhill direction, you'd be right. Here's an example of some creepy tombstones in an old cemetery in Harper's Ferry, West Virginia, and they've been basically rotated in a downhill direction. Notice that because tombstones are not alive, they can't grow back into an upright position. So basically, unless someone fixes them, they're eventually going to tip over. Thanks very much for your attention. This has been another Smart Figure.
So here's what happens with solidification, where, yeah, the layer thaws in summer, it gets saturated and sort of flows, but It's held in place at the bottom by the permafrost and at the top by vegetation. And so you get these weird lumpy structures where it sort of flows underneath the layer of vegetation. And that is the end of the chapter, which is excellent. So I need to have you guys do the student evaluation. So I need a volunteer for this because I'm not allowed to actually be involved. So I'm gonna pack up and head out. Everyone make sure you've signed in so I'm not influencing you.